So here for this video, we will discuss the second part of the 2.1, which is on the homogeneous equation. In the previous lecture, we discussed the separable differential equation, the first order separable differential equation. So now, the second type of the first order differential equation, is called homogeneous equation. This actually is quite related to the separable differential equation. So meaning to say that to understand this, you have to understand the separable differential equation first. Why? We'll see after this the method of solution. First of all, let's see the definition of the homogeneous. So actually this one I just keep this very simple, because this one actually you have learned about the homogeneous function from the calculus class, or maybe from the foundation, or maybe from the SPM level. Homogeneous means of the same kind, and this is by definition. Homogeneous means that the same kind or uniform in nature. So let's see, you have a function f in terms of x and y, and this function is called homogeneous function of degree n if for any parameter t. Let's see, you have the original function fxy. Let's see, you replace the x in the function in the original function by tx, and the y variable by ty. What happened next is that you can factor out the variable t to the power of n, and this the common factor here is multiplied by the same function given to you, the original function f of x and y. So if you can do like this, means that this function f is homogeneous function of degree n. Actually there are so many definitions for the homogeneous. This one I just take one definition for the homogeneous function. We can also check the homogeneous by inspection. Later I will show you how to show the homogeneous equation by inspection. So by this definition, homogeneous is not exactly the same function. Homogeneous means that same form of the function, same kind of function. For example, let's see your f1, let's see your f here is a linear function, and your g also a linear function, means that these two you can call as a homogeneous function. But make sure this the function must be in the same degree of the linear function. So I will show you this. This is the calculation by using this definition. This is only the calculation, so I don't want to explain more, because this one you can just refer to this slide, because this is only to prove that whether these two are homogeneous or not. By using this formula, f of tx ty means that if you have x square plus y square, means that the x here you replace by tx, the y you replace by ty. And let's see what happened. When you do the calculation, like this, then you can see that you manage to factor out the common factor t square from this equation. Then you see here from after you factor out the t square, then you can see that the remaining factor here is exactly same as the given function. So therefore this function is homogeneous of degree 2, because this is t square. Where the second function here is x to the power of 5 minus y to the power of 3. If you do the same method, you replace x here by tx and the y here by ty. But what happened is here, after you do the expansion, the calculation, you can see that from these two we can manage to factor out the t cube, the common factor t cube. And what happened here, this remaining function is not exactly same as the given function. So therefore this one is called non-homogeneous function. This is by calculation. However, in this topic, if we don't want you to show these two calculation, so the best way is actually to check by inspection, whether it's homogeneous or not. Normally by inspection we just refer to the power, for the function. For example, here you have two variables here, x square and y square. So if you see that each variable here, each term here has the same power or same degree, then you can see that this is homogeneous, because this one x square, the degree is 2, the y square, the degree also 2, then it's the same degree, means that this function is actually a homogeneous function of the same degree 2. Where this one, by inspection, you can see, okay, by referring to the power here, x to the power of 5, this is y to the power of 3. This one is the term with degree 5. This one is also the term with degree 3. Then this is not considered as the non-homogeneous because not the same degree. Okay, 5, this one 5, this one 3. Okay, so it's actually by inspection you will know whether it's the homogeneous or not. Okay. Okay, now, so let's see how to define the first order homogeneous differential equation. Okay, so first order differential equation, okay, in this form, m of xy, okay, dx plus n of xy dy equal to 0, okay, is said to be homogeneous if both function m and function n are homogeneous function of the same degree. Okay. So to know whether this equation is homogeneous or not, you have to double check the function, the coefficient function here, this m and this n. Okay, check whether these two homogeneous or not. And not only homogeneous, these two must homogeneous of the same degree. Okay, okay, let's see example. Okay, so the first example here, okay, you have x square minus 3y square dx minus xy dy equal to 0. Okay. So this is homogeneous differential equation. Okay, the reason why, because if you look at this function here, x square minus 3y square, you can see that this is x square and then this is y square. So the same power, the same degree. So this is actually the homogeneous function of degree 2. Okay, where this one is x times y. Okay, now in terms of the two product of two variables here, okay, to calculate the degree, you have to add the power for these two. Okay, so this is x to the power of 1, y to the power of 1. So the degree of this is 2. Okay, so you can see that, okay, this is degree 2, this one also degree 2. So that's why it's homogeneous differential equation, because, okay, these two have the same degree of homogeneous. Okay. Okay, the second example is that, okay, for the non-homogeneous, for this equation, okay, x minus y plus 1 dx minus x plus y dy equal to 0. Okay, so this is non-homogeneous because if you look at this function, x minus y plus 1, okay, this is x to the power of 1, y to the power of 1, but the constant is the power is x to the power of 0. The power is actually 0. Okay. So this one is power of 1, this one is 0, so it's not homogeneous. It's not the same degree of x. Okay, so this one is not homogeneous. Okay, so because of this, the whole equation here is considered as non-homogeneous differential equation. Okay, no need to double check this one. Just check this one. If this one not homogeneous, then everything will be not homogeneous. Okay, okay, now the third one, also non-homogeneous. Okay. Because you can see from this equation, this is okay, x times y. Okay, this one means that 1 plus 1 is 2. So the degree here is 2. Okay, this one also 2. So it's the same degree. So it's considered homogeneous, degree 2. Okay. However, here this is x to the power of 1 and this is y to the power of 1. This is homogeneous, degree 1. Okay, so it's not the same degree. So that's why it's not homogeneous differential equation. Assalamualaikum and good day, student. So, okay, now we discuss, okay, what is the method of solution of homogeneous equation. Okay, so let's see, you are given a homogeneous equation, m of x, y, dx plus n of x, y, dy equal to 0. Okay, so this homogeneous equation, okay, can be transformed into a separable equation by using an appropriate substitution. Okay, so meaning to say that to solve the homogeneous equation, okay, we have to use the appropriate substitution. Okay, and after you use the appropriate substitution, this homogeneous equation will be transformed to separable equation. Okay, and once you get the separable equation, then we can solve using the method of separable variable, okay, to solve the equation. Okay, so what is the appropriate substitution that we can use to solve the homogeneous equation? Okay. Okay, now since that we have two functions here, m and n. Okay, so the method of substitution. Okay, there are two formula. Is either you can use x equal to vy or you can use y equal to ux. Okay, because in this form, if you are given the differential in this form, the main problem is that okay, in terms of dx dy, we don't know which one is dependent variable, which one is independent variable, because this is not given in terms of dy over dx or dx over dy. Okay, if the equation is written dy over dx, then we know y is dependent and x is independent. Okay, but here they just put dx dy in the form of differential form. Okay, so in this case there are two options. Okay, it's either you want to let's see, the first formula here, we assume that x is dependent variable. So we need to replace all the dependent variable x, the x and all the dx here into in this equation, okay, by using this formula. Okay, so you replace x, okay, by this formula vy, okay. So from okay, x is dependent, okay, y is independent. So we introduce a new variable v, okay, in between of these two, okay. And then after that, okay, by using this, then we can differentiate the differential dx from here. So how to get this formula is actually using the product rule. Okay, the product rule uv. Okay, we can see that v differentiate y, get dy. Okay, plus y differentiate the v dv. Okay, so this is in terms of the differential form. Okay, by using the product rule. Okay, so actually this one no need to memorize lah. This one is just need to know this formula only. Okay. And the second formula is to replace the y. Okay, let's see, y is dependent variable, y equal to ux. So y dependent, x independent. So we introduce the new variable u. Then once you get this, you have to calculate the dy because we need to replace y and also the differential dy. Okay, so how to get this formula? Also using product rule. Okay, so product rule u differentiate the x, okay, in terms of differential form dx. Plus x differentiate the u, we get the du. Okay, so there are two formula here how to solve the homogeneous equation. It is up to you whether you want to use the first formula or the second formula. The one that I mentioned here is just a guideline. Okay, meaning to say that if your m, the function m here is simpler than function n, then we can use this formula. Simpler means that maybe that function m here, maybe the term is less than the function n. Okay, so if m simpler than n, so better use the x equal to vy because we can replace the dx, okay, much more easier. Okay, if you use this formula. Okay, and if the second one is another option here, you can use this if n is simpler than m, means that this function is simpler than m. Then we can easily replace the dy by using this formula. Okay, but overall actually it is up to you. You can use this, okay, or this. Okay, it is up, you can decide. Okay, it just like to give you the hint is that if you use x equal to vy and then put back into the equation and then you feel that it's become very complicated, then the better idea is that you switch from this x equal to vy to y equal to ux. It's just like, okay, in terms of the computational solution, maybe when you use this one, maybe longer calculation than this. Okay, so it is up to you actually. Okay, okay, don't worry about this one. Okay, you can choose x equal to vy or y equal to ux. Okay. Okay, so let's see the example how to solve the homogeneous differential equation. So let's see you are given this differential equation x minus y dx plus x dy equal to 0. So we want to solve this homogeneous differential equation by using an appropriate substitution. Okay, you can see that this is homogeneous because x minus y, this is x to the power of 1, y to the power of 1. This is the homogeneous function of degree 1. And this one also x to the power of 1, also homogeneous, degree 1. So this same degree, homogeneous. So that's why it's become homogeneous differential equation. Okay. Okay, now we want to solve this using appropriate substitution. Okay, so just now if you look at the previous slide, okay, you can use this formula. Either you want to replace x or you want to replace y. Okay, if you want to replace x, then the formula is x equal to vy. Okay, if you want to replace the y, then the formula is y equal to ux. Okay, so here I will use the formula y equal to ux. Okay. Because if you look at this x minus 1 compared to the x, this much more simpler than this. Okay, because this is only one term. Okay, this one involves two terms. Okay, so it's better for me, okay, to replace the y lah, because this one involves x dy. So I'm using the formula y equal to ux, so that when I calculate the dy, this is the formula. Okay, then it's easy for me to substitute the dy here. okay, and then multiply by x, okay. Unlike if I replace, if I'm using the second formula, the x equal to Vy, then I need to replace here, then the calculation, maybe you have to do more calculation, okay. So, but still okay, if you want to use x equal to Vy, it's still okay, you'll get the same answer, okay. So this is my y equal to ux, this is the dy. Then what you have to do next is to substitute y, replace the y and the dy here into the equation, okay. So you have this, so x minus, this is your y, okay, replaced by ux, and this is the dy, okay, equal to 0. So you need to simplify, okay, simplify this one. I open the bracket, become ux dx, and then this is x squared du equal to 0. Then I combine the same term du with the du, dx with the dx. So this one dx, dx. So you have x minus ux plus ux. So these two become 0. Then this one become x dx plus x squared du. So you can see that after you substitute y and dy into the homogeneous equation, okay, by using this substitution, so we can transform this homogeneous to separable differential equation, okay. So once you get separable, then you can use the method of separating the variable. So here you can separate the x and u here because there are two variable x and u, okay. So this one from the separable differential equation here. So first of all, x, this one I can, okay, the x dx is okay. Then this one x squared du, so x squared should be here, should be together with this, okay. So all divide by x squared become 1 over x dx, and this one become 1 du, okay. So it become move to the other side with the negative du. Then okay, integrate both sides with respect to the variable here, okay. This one integrate with respect to dx, and this one integrate with respect to u. Then integrate here, you get ln x. This one you get negative u plus c. So after that, this is the solution for this separable differential equation. So to get the final answer, you have to replace back the u here in terms of y and x. So just now we use y equal to ux. So the u equal to y over x. So replace back in terms of y and x. So the final general solution here is the solution for the given homogeneous equation. Okay. So the next example, okay, to solve the homogeneous equation. So let's see, you are given this equation, negative y dx plus x plus square root xy, okay, dy equal to 0. So this is the homogeneous equation. Okay, you can double check by inspection, okay, whether this is homogeneous or not, okay. Okay, now we want to solve this by using an appropriate substitution, okay. So in this case, I'm using this substitution, x equal to Vy. Okay, again, why I'm using this substitution, because according to the function here, the negative, this one, the m, okay, this is the function m, this is the function n. So you catch here, the function m is much more simpler than the function n here, and this function m together with the dx means that I have to use the formula x equal to Vy. So easy for me to use this formula x equal to Vy. So that when I substitute the dx into this, so easy for me to expand one by one compared to this one. Okay. So yeah, but if you want to use y equal to ux, yes, you will get the same answer. It's just like in terms of the calculation may be longer, in terms of the integration may be more complicated than this. Okay, so you can try. Okay, but at the end you will get the same answer. Okay. Okay, I'm using this one. Okay, so I substitute x equal to Vy. So the dx from here is v dy plus y dv. So put back into this equation. So this is the dx. And whenever you see the x, you have to replace. Okay, so x here Vy. So x, this one x replace Vy times y, get Vy squared. Okay, so this one I simplify because y squared is equal to y. So y here. Okay, y square root v. Okay, now and then you open the bracket, simplify, expand everything. Okay, and then combine the dv with the dv and the dy with the dy. So this one will be okay. This one negative vy dy. Okay, okay, and then okay minus y square dv. So this one, okay, and this one v plus vy dy. Okay, this one actually combined with this, you get 0 actually. Okay, 0. So you only get this part only, okay, y square root v dy. So this is actually the separable differential equation, okay. So after you get this, then you can separate the variable y and v. So according to this, so you can see that according to this differential dv means that all the v should be here, okay, all the y should be here. So now, okay, since that this you have the square root v here, okay. Okay. Then you do the separating the variables, okay, so become 1 over square root v dv, and this one move to the other side, become y divided by y square, okay, become 1 over y, okay. Since that I move this to the right hand side, so there is no more okay, negative here, become positive, okay. Then you integrate both sides with respect to the variable. So this one 1 over square root v is v to the power of negative half. Okay, integrate this, you get 2v to the power of 1 over 2. Okay, this one is by using the basic integration. And this one is the integrate 1 over y, you get ln y plus c. Don't forget the c here. Okay, then after you get this, this is the solution for separable, okay, differential equation. Okay, that you transform from the homogeneous. Okay, then once you get this, you have to replace back. Okay, replace back the v in terms of x and y. Since that the v here, the x equal to vy, so the v is x over y. So it's square root x over y, okay, times 2 equal to this, okay. Then this is the final answer for the solution of homogeneous differential equation given by this equation.